Bienvenidos, Ushamdi, and welcome. CMIT 454, sections 6380 and 6382 for the first 8-week term of the spring 2018 semester at the University of Maryland University College. This is the Cisco Networking Academy CCNA Security version 2.0 course, and this morning's Packet Tracer tutorial and solution set is going to be on Packet Tracer activity 8.4.1.2, where we're going to do a deep dive review of Site-to-Site IPSec VPNs. And this was all about Chapter 8. Now, let's go ahead and dive in and take a look at the topology that we're going to be working with here. Now, as you can see, and this is one of the questions that learners have often, is, well, would I do something like this? Would I set up an IPSec VPN tunnel in my internal network? And the reason I say internal network is look at all these addresses that we're using here, right? Or I should say all these networks: 192.168.2, 192.168.3, 192.168.1. So these are all RFC 1918 addresses, right? Which means they're not routable on the public internet. You can see we have no public internet presence here. Now, remember, the context of this course, as well as this activity, is CCNA. It's entry level. So while we're going to be setting up this IPSec VPN tunnel, we're more interested in the steps that are required and the settings that are available than we are showing a diagram here that represents the entire internet, right? Or like, you know, this being the internet cloud, and we'll come back to this drawing as well, you know, this being the internet, and you know, this is your ISP, internet service provider, and you're connected. Maybe this is your office in New York City, and maybe this is your office in Santa Rosa, California, right? So, and then we want to communicate from this subnet to that subnet, or in other words, we want the people in the New York City office to be able to communicate with the people in the Santa Rosa, California office. Then we would have this IPSec VPN tunnel. As it's presented to you here, right, this is more for acclimating you or introducing you to how we do these things, how we set these IPSec VPN tunnels up without the additional complexity of NAT, the additional complexity of, you know, this ISP out here. So again, one of the questions I get right out of the gate from learners is, why would you do this? And in reality, this is probably not something that you would deploy in your enterprise environment. Now, there may be a corner case, but I'm saying in general, think of it like this as we're working through this activity. Think of it as like this is the ISP network, right? And that this is your New York City office, and this is, I'll say, San Francisco, right? So think of it like that, and that's what we're trying to do. And we'll just ignore the fact that the addressing here and the addressing here is using these 10.2.2 or 10.1.1.1.0/30 over here, right? That they're not using what we would commonly associate with internet addresses. And I'm going to talk more about use cases as we go forward here. Now, crypto maps. So we're going to be doing this using crypto maps, and crypto maps was definitely sort of the original way to approach the IPSec VPN tunnel between not only sites, but between VPN devices like routers. We would use a crypto map, and this was something that was commonly done. And I'll make reference to something called a static virtual tunnel interface, or SVTI, which is sort of the newer incarnation, because the way that it went was we had crypto maps, which is what we're going to be practicing here, right? So we do it with a crypto map, and definitely good to know how to do it, because you still see a lot of implementations around that use crypto maps for whatever reason. Maybe that's the admin is familiar with that and that's what they're comfortable with. The second iteration, and this was also covered in Chapter 8, was to use GRE. And so you may be asking yourself, well, why, and I should say GRE and IPSec. You may be asking yourself, well, why would I use GRE and not the crypto map? Well, remember, the crypto map has no support for, I'll just put BCast, for broadcast or multicast. So if I wanted to establish between these routers, and again, we're going to say this is New York, San Francisco, if I wanted to establish an OSPF adjacency to run a routing protocol or EIGRP, I couldn't do that with my crypto map. I would need a tunnel that supports multicast, and that is where our friend GRE comes into play, because GRE does allow you to do multicast as well as broadcast. And again, if it does broadcast, it'll do multicast. So that's where the GRE came in. Now, both of these are point-to-point, right? They're both point-to-point. The most recent incarnation is called an SVTI, and I'll show you some more information about this as we move through the activity. The static virtual tunnel interface, right, which uses no GRE. It is point-to-point, so I'll say P2P, no GRE required, it is point-to-point, and no crypto maps, right? And you'll see the crypto map we do is pretty straightforward, right? It's just an ACL, but again, those can become very annoying very fast. And here, there's no crypto maps. And you can see there was a big movement to get away from the crypto maps. And all the crypto map is an ACL. It's an extended ACL that we're going to create. And so this has been sort of the iteration in terms of point-to-point solutions for IPSec. Having deployed all three of these, there is no question in my mind that the SVTI is by and far the easiest of these three to set up. It is super, super easy. And so we're going to be doing the crypto maps, right? Remember the chapter talked about GRE IPSec, and now today, the most recent implementation of a point-to-point IPSec tunnel that you might be interested in is an SVTI, a static virtual tunnel interface. No GRE, no crypto maps, point-to-point, right? So let's dive in here, and again, let's get a great foundation going as to how we would move forward, because a lot of the things that you do in all three of these, you're going to see right over here. So it doesn't matter whether you're doing a crypto map or GRE IPSec or SVTI, you're still going to be doing your phase one. You're still going to be doing your transform set. It's once you finish the phase one settings and the phase two settings with the transform set, it's once you finish those things, that's where the little differences will come into play, right? And again, very minor differences, but we have to know these foundational topics that we're working with. Now, if we look, we're going to verify, whoops, I didn't want to do that. We're going to verify, why is it doing that? There we go, connectivity throughout the network. We're going to configure router 1 to support a Site-to-Site IPSec VPN with router 3. Now, another critical point, and learners become very confused with this. VPN. You see these three letters here, VPN, and I cannot stress this enough, and they're right here in the center of the screen. When you say VPN, that does not imply encryption. And this is a common point of confusion. You'll hear people, it's used in that context, right? It's used in the context of, oh yeah, well I'm VPNing in from home to the office. And yeah, when you say it like that, there's a pretty good chance you're using encryption. However, when I say virtual private network or VPN, right, it does not imply, right, it doesn't mean that you have to have encryption. Let me give you some examples. MPLS Layer 3 VPNs. All this does is provide segregation of routing information via what's called a VRF, a virtual routing and forwarding instance. There is no encryption. This will work. MPLS Layer 3 VPNs will work fine, right? And that's typically how they do work, is there's no encryption at all. So if you're working with a service provider like an AT&T or a Verizon or a Level 3, and you have MPLS service with them, and it's an L3 VPN service, chances are you have no encryption between that's being done on the MPLS layer 3 VPN or the MPLS cloud that the provider has. And the same thing is true of DMVPN, which the course touches on, right? And this, I'll put a little asterisk here, this is where you make your money in the IPSec VPN world with Cisco. So dynamic multi-point VPN. It uses multi-point GRE, right? So not regular GRE like we saw when I talked about GRE and IPSec. It uses multi-point GRE, and it uses this thing called the Next Hop Resolution Protocol. Now, and you do use IPSec settings as well, but by default, right, I can run DMVPN, and DMVPN is really made to run over the internet, right? I can run it with just multi-point GRE and NHRP and be done. Now, you'd be crazy to do that because your traffic would not be encrypted, but DMVPN doesn't have to have IPSec or any type of encryption. So here's two technologies, and these are massive technologies in the networking world that have VPN in the name, but do not require encryption. So make sure you're aware of that, because I've sat in meetings, MPLS L3 VPN to be specific, where management individuals as well as technical individuals made the statement that, oh yeah, we can use the MPLS layer 3 VPN because it's encrypted. And I've had to say, well, hold on a second, I don't believe that that's the case, because MPLS L3 VPN, by default, right, there is no encryption running over that MPLS L3 VPN. It's simply virtual routing and forwarding instances. And think of these as just like VLANs. VRF, think of a VRF as a layer 3 device. It's the same as a VLAN, which is something we see at layer 2, right? So that's all a VRF is, except it's at layer 3. It segregates the traffic just like a VLAN does at layer 2. It segregates it at layer 3. But there's no encryption involved at all. So be aware of that and be careful when you use those terms, right? And again, context is key and use case is key. Obviously, if you're talking about IPSec VPN with somebody and you're just saying VPN, no harm, no foul. But be careful when you talk about MPLS layer 3 VPN and the misconception. You'd be amazed how many people are under the impression that when you say DMVPN, that they think it has to have IPSec. And that is not the case. It will run without any problems, just as DMVPN without IPSec, right? All right, let's go ahead. I want to make sure I give you that background because these are critical things that you don't see in the chapter. And again, for obvious reasons, a little out of scope, but I want to make sure we cover those because in the real world, these things do come up. So, all right, so here we have our IKE. Oh, okay, and I can see that they've already set me up here. So take a look at this. And again, these terms become very confusing. So when I say IPSec, I want you to think of IPSec as a big umbrella. And underneath this umbrella, right, we have all of the protocols and everything that we're going to be using that make IPSec possible. And so under this IPSec umbrella, we've got different protocols. You have ISAKMP. You have what they call IKE, right? We've got encapsulating security payload. We got authentication header, right? So all of these things fall under the umbrella of IPSec. And this is what makes IPSec so scalable and so flexible is, let's say that, technology X comes along that does super encryption. Well, we can simply add that under the IPSec umbrella and then integrate it from that perspective. And so IPSec is kind of the overarching ecosystem, so to speak, of all of these security protocols, some of them for authentication, some of them for confidentiality, right? Some of them for integrity, and they all fall under the IPSec umbrella. And these terms get conflated all of the time or confusing all of the time. And this doesn't help, right? So take a look at what we see here. See ISAKMP Phase 1. But then here it says IPSec Phase 2. And then I think further down I saw, yeah, we see, and then so down here it changes and says IKE Phase 1. Right? And I'll bet you that it says IKE Phase 2 down here. So when learners see things like this, it becomes really confusing because you look at this and you say, oh, so this must be the ISAKMP Phase 1, but why does it say IKE Phase 1 ISAKMP? And this says IPSec Phase 2 policy parameters. Why does it down here further down say IKE Phase 2? Why not IPSec Phase 2? And so here's the key to understanding these terms. Think of it like this. When we're discussing phases, ISAKMP Phase 1 is the same thing. Actually, I guess I'll do it this way. Let me get rid of these guys over. And actually, I think I can go, can we pull these back? All right. So oh, there, okay, it was working. It was a little slow. I'm trying to pull that back. There we go. So when you see IKE Phase 1, that's synonymous with ISAKMP Phase 1. These mean, in the context of the phase conversation, they mean the same thing. So you can say IKE Phase 1 or ISAKMP Phase 1. I like to use IKE. It's just easier to say IKE Phase 1, IKE Phase 2, right? But when you say IKE Phase 1, you are implying ISAKMP Phase 1. When you say IKE Phase 2, and I'll just put IKE Phase 2, you're saying ISAKMP Phase 2, right? So IKE Phase 1 and IKE Phase 2 are the same as I'm getting tongue twisted here. IKE Phase 1 and ISAKMP Phase 1 are the same thing, just as IKE Phase 2 and ISAKMP Phase 2 are the same thing in the context of the phases. Where this becomes confusing, and I thought the chapter did a great job on this, is that there's an IKE version 1 and an IKE version 2, right? And so this is where it can become a little confusing. And the chapter did a beautiful job describing the IKE v2, right? And the differences. And remember, some of those key differences that you're going to run across is one, there's a keep alive mechanism here that's built in with IKE version 2. So those are the similarities, right? But don't confuse IKE version 1 and version 2 with IKE Phase 1 and Phase 2. These are separate concepts, right? These are different concepts. We've got the versions of IKE, and then we have the phases. And know that IKE Phase 1 and ISAKMP Phase 1 are the same thing. IKE Phase 2 and ISAKMP Phase 2, it's the same thing. And it would have been nice had in this activity they've picked one and stuck with it. Right, but you can see they didn't. They use ISAKMP Phase 1, they use IPSec Phase 2, then they come down here and they say IKE Phase 1, ISAKMP, and I think further down it says IKE Phase 2, right? So remember, those are the same, these are the same. It's the versions here with IKE that are different. So let me clear that, and let's finally dig in here. And I apologize, I want to make sure I give you that background because those are details that are critical that hopefully provide some clarity around what you're reading over here on the right-hand side. So we're going to test connectivity from PCA to PCC. We want to make sure that things work right now. So let's go ahead and say ping 192.168.3.3. We may have to ARP here for our default gateway, so we may request timeout, but then it's going to work, right? And everything worked great right there. And let's go backwards. Let's make sure we don't have any ACLs that are maybe allowing the echo replies to come back through, but blocking PCC. And what are we doing? Ping 192.168.1.1. And there we go. So we've got connectivity right out of the gate. Everything looks really, really good. So what is our next step? And again, this is one of the most important steps. Enable the security technology package. We've had a couple learners this semester already who have emailed saying, I'm trying to run the zone-based policy firewall commands, and they're not there. And my first question is always, well, did you, hold on, let me get this in, Cisco Con PA 55. I said, did you apply the license and reload the router? And these are not mutually exclusive tasks when we're activating the right to use license. So here I am in user exec mode as evidenced by the greater than sign. If I type enable or just EN and hit enter, this is going to transition me into Cisco ENPA 55. CISCO ENPA 55. This is going to transition me to privilege exec mode. And it's from here that I could say show version, and at the end, take a look. We've got our licenses, and we probably remember this from the zone-based policy firewall discussion. So you can see where I've got an IP-based license, and again, that's just sort of the basic license for the router to be able to function. And then I've got the security and the data. Now, in reality, on a real Cisco router, and I just happen to have this one here, and we may, and I'll come back, I'll let that think for a second. It takes us a couple seconds, so I don't want to waste any time. So on a real router, you'll see that you can also say, and I think you can do it here, I think it's just the syntax here, it doesn't like show license by itself. On the real router, you can say show license and it's going to work. But here I'll say show license all, and you can see license store, the evaluation license storage, and here it is, feature security K9, the license type is eval, it says it's active, right? And you can see we've got an evaluation period. But this is, again, this is Packet Tracer kind of staging this for us. Like it's here, but this is not what you would see on a real router. And I'm hoping that, yeah, there we go. That's not what you would see on a real router that, that doesn't have the license, right? So you can see that this router here, I actually purchased the license. I have the Security K9 license, so it's lifetime, it's permanent. And this is what you see, right? If it doesn't have the license, and I don't know if I actually have a router that does not have the Security K9 license. Let's check it out. Yeah, no, that one's permanent as well. We'll check one more and then we'll just move on here. And show license, whoops, show license. All right, I think I've purchased, I guess I have the license for all of mine. So again, what you would see is it would tell you that it's not active, right? You wouldn't see something like this here that shows you that you've got this eval period if you haven't done and accepted the right to use license. So let's go ahead and do that. I'm going to go into global config with the configure terminal command. We're going to say license boot module C1900 technology package security K9. And again, what this is going to do, it's going to present me with that prompt that we're going to see. It's going to give me this huge legalese statement, and there it is. And you know, your acceptance says that you're going to do these things like you say you're going to do them. And I say yes. Now, here's where most students will become confused. They'll say, oh, I've applied the license, so where's my crypto IPSec command, right? Or where's my crypto ISAKMP command? Or where's my crypto map command? They're not here, right? And the reason that they're not here is because what we need to do now is save our configuration and then reload the router. And you can see it's very quick in Packet Tracer, and this is one of the beauties of Packet Tracer, is that we won't be here for about 3 minutes waiting for the router to come back up. We type in reload, and look at that, we're back, right? Just that fast. So Cisco con PA55 for the password at the console. We're at user exec prompt. We say enable to get to privilege exec, Cisco ENPA55. You can see that OSPF has come up, and that's how we're providing reachability between router 1 and router 3. It's via the open shortest path first routing protocol. We're going through router 2 to get there. So now I'm back in privilege exec mode. I say show license all. And you can see, we see that same information. It would be different on a real router. When I say show version, you can see, so basically Packet Tracer kind of has it with the show license command, it has it pre-canned, like ready to go, but it forces you from an activity perspective to put in this command, because this command is needed if you don't have that security license. You would have to do something like this on your ISRG2. So you can see now that we have an evaluation license. It doesn't say disabled, right? It doesn't say none. It says security K9 eval license. So now when I go into global config with the configure terminal command and I say crypto and do a question mark, now I see the IPSec, the ISAKMP, and the map options. Again, we have to do the license addition, or I should say the license acceptance is technically correct because we're not adding the license, we're just accepting the right to use piece. So we have to accept that, or else none of the crypto commands that we need are going to work. All right, so now let's move forward here on router 1. So the first thing we need to do, we need to identify the interesting traffic. And what do we mean by that? Well, with the crypto map, and only with the crypto map, I have to say that this is the interesting traffic. This is the traffic I want to encrypt. And the reason you have to identify the interesting traffic is because we'll be applying the crypto map to the egress interface here, the outbound interface, right? And by outbound, I mean traffic that's going to be going this direction. We're going to have to tell the router, I want you to encrypt traffic with this source and destination pair, and everything else don't encrypt. Because remember, if it encrypts it and it leaves in this direction, and it was going to this LAN segment over here, and we're not doing, we don't, because the other crypto map is going to be on router 3 here. And so this is where we have that IPSec tunnel. So traffic that flows between router 1's LAN and router 3's LAN, that is going to be encrypted. Traffic that goes from the router 3 LAN to router 2, or from the router 1 LAN to the router 2 LAN, so from 3's LAN to 2's LAN, or from 1's LAN segment to 2's LAN segment, that traffic, we don't want that traffic encrypted because, why not? Yeah, because router 2 has no clue how to decrypt that traffic and get it over here to the PC or to whomever else may be hanging off over here. Router 2 has no clue how to decrypt that traffic because it's not participating in this point-to-point crypto map, right? And this is, again, it's a point-to-point solution. It's between router 1 and router 3 exclusively. So we can't send encrypted traffic to router 2 expecting router 2 to be able to unencrypt that traffic, decrypt that traffic, and then make a routing decision based on that, right? It's not going to happen. And so the crypto map that we apply to this serial interface here and this serial interface here on router 3 and the serial interface here on router 1, that crypto map that we're going to lay on top of that interface is going to reference the ACL and look at the source and destination definitions in the extended ACL to determine whether or not it's going to encrypt that traffic. And you'll see, and this is a great activity, phenomenal activity, because the reason you're probably looking at this saying, well, why do they have the router 2 LAN up here? Why is this even up here? Because we're not sending encrypted traffic there. That's the whole point, is we need to be able to demonstrate, one, we'll put down here number 1, can I send encrypted traffic between these LAN segments? But then number 2, can we send unencrypted traffic with the crypto map here and prove that the crypto map is not encrypting traffic between router 1's LAN and router 2's, or router 3's and router 2's? And so that's why router 2's here, right? And that's why we've got we have the LAN segment over here behind router 2. All right, so let's pull back up router 1. Let's pull back up router 1. And we are in global config, and we now see all these options. So first things first, we need an extended ACL. So access list 110. Now, when we say permit, think of it as match, right? In this context, with defining the interesting traffic or identifying the interesting traffic, we are interested in matching that traffic. So I would say access list 110 permit IP. Remember, we're not saying TCP, we're not saying UDP, we're not saying ICMP, we're saying all traffic. And IP encompasses every possible form of traffic. So we say permit IP from the 192.168.1.0, and remember we need a wildcard mask there, not a dotted decimal subnet notation with the 000.255. That is a wildcard mask. So all traffic from 192.168.1.0 to 000.255, which is the wildcard mask for the subnet, /24, and going to the destination 192.168.3.0, 0.0.0.255. That is the traffic I'm interested in matching. And basically in English, that just statement says permit or encrypt any traffic, right? Match any traffic for encryption that is coming from router 1's LAN segment going to router 3's LAN segment. And we're putting this is on router 1. On router 3, we're going to do the exact same thing, but just in the opposite direction. So now we come down to, and again, this is, if you're new to this, this is definitely one of the more confusing things. And the best way to practice this is to simply do it over and over and over again. Repetition, iteration, right? So now we're going to be doing the IKE Phase 1 or the ISAKMP Phase 1. IKE Phase 1, ISAKMP Phase 1, we're saying the same thing. But what is IKE and ISAKMP Phase 1 all about? Well, it's all about protecting the keys. We're going to be sending these keys between the routers, right? And you can see here we're doing a pre-shared key. There's other keys you can use, but pre-shared is very popular. It's very, very easy to do. So crypto ISAKMP key, we need to be able to protect that information. And so that's what the IKE, and I'll keep saying IKE ISAKMP, the IKE/ISAKMP Phase 1 is all about. It's about how do we protect the keying material that will be used to set up the IPSec tunnel. Now, you'll notice that they don't mention or say IPSec as part of Phase 1 at all. And that's because it's not. IPSec is not part of your Phase 1. IPSec is the Phase 2 piece. But in order to ensure the confidentiality and the integrity and the authenticity of the keying material, to protect it, we have to do these Phase 1 settings, right? Because this protects our keying material. So let's put these settings in here. So I'm going to say ISAKMP, and what do they have up there? I'm sorry, crypto ISAKMP, sorry. Crypto ISAKMP, and the policy number was what I was looking for. And policy 10, you can see, I think you get up to 1,000, yeah, or 10,000. So we're going to go with crypto ISAKMP policy 10. Now it's in here that we have some decisions to make. Now, what type of encryption do we want to use? Well, we're going to use AES 256, right? And I'm going to talk about the defaults here in just a second. For authentication, right? How are we doing the authentication? Well, remember, we're using a pre-shared key. And that is the key that we're going to be defining once we finish with the Phase 1 settings, which these are the Phase 1 settings. And then we get to something that's very important. The Diffie-Hellman group, and I'll do group and question mark, and you can see here. For packet tracer, this is great. This is fine for packet tracer, right? Because it's all about getting the process down, right? The muscle memory where, yeah, okay, I know I say crypto ISAKMP policy number. I get in here, I set the authentication, I set the Diffie-Hellman group, but maybe I do a lifetime value, I set the hash. For all of my Phase 1 settings, however, and in the reading, you should have seen this, where Diffie-Hellman, the group 1, 2, and 5, these have been antiquated, sort of sunsetted, not used anymore, deprecated since, I think, 2012, I want to say. So these are extremely old, and you do not want to use 1, 2, or 5. If I was to pull up the real Cisco router here, and I think we're on router 15, and go into privilege exec and global config and say crypto ISAKMP policy 10 and do the question mark, you can see we have just about the same options to choose from, if not exact. I think that's exactly the same, is it not? Yeah, I think authentication, encryption, group hash. Yeah, everything looks pretty much the same. So we've got all of the same settings. If I were to say group, I want to expose you to this early. Yeah, so there's more than 1, 2, and 5. And you can see 1 is only 768 bits in terms of the key length. 2 is 1024, and 5 is 1536. But again, you should never, ever, ever be using 1, 2, or 5. So if you're asking yourself the question, well, Travis, hold on a second. Why does Cisco even have them there then? Why do they put them there so that I could make the mistake possibly of using 1, 2, or 5 because I don't know any better? Well, the reason they're there is for backwards compatibility, because not all routers, and this is going to be an odd statement. So not all routers support, or not all Cisco routers support Diffie-Hellman Group 24. And let me clarify that statement. So as soon as I say that, you're probably going to say, oh, that's not true because anything running iOS 15 does. Well, yeah, but what about the routers running 12.4 code? Right? Because maybe you've got a scenario where you've got an older router for whatever reason, you can't get it upgraded and it's just out there and it's running a legacy version of code. And you want to do a site-to-site IPSec VPN tunnel. And this happens all the time. In fact, I know I've had learners that have worked for some pretty large companies that have 2600 series routers in the field. Right? And those are super, super old. I mean, I think they were end of life, end of support, end of sale in like 2005, right? So again, they're here for backwards compatibility, for legacy support, because you may not have two brand spanking new 2911s or 3945s, right? You may have a 3945, but then it's going to a remote site in Siberia and they're running an 1841 or a 2811, right? And maybe it doesn't have Diffie-Hellman group 24. Now, another key takeaway here is, and this is a generalization, but it's 99.99999% of the time a true statement. When we're dealing with encryption, right, and we're dealing with IKE ISAKMP Phase 1 or IKE and ISAKMP Phase 2 settings, it's the opposite of spanning tree. Remember with spanning tree, lower is always better and there's never a tie, right? With encryption and IPsec, in terms of the bit length for keys and the options we have to choose from, larger is always better, right? It's larger is always better. So group 24 is better than group 21, is better than group 20, is better than group 19, is better than group 16, 15, so forth, right? And so you can see this, I think, is using elliptical curve cryptography here for group 21. But 24 is, again, generalization, that's the one that you want to go with. The larger the number, the better, especially in the size of the bits in the key, okay? All right, so other options to choose from, make sure you're aware of those. In the real world, you would never, ever, ever choose group 1, 2, or 5. But this is packet tracer, right? And we're just trying to get the muscle memory down as to how we would do this. So we're going to go with group 5. Now I'm going to exit, and we need to get the key in here. So this is where I'm going to say crypto ISAKMP key. This is my pre-shared key, VPN PA, and be very careful that you get this key correct. It has to match. And that's another key statement. Not only does the key have to match between the two routers, all of the settings, and there's one exception, and I'll talk about that, it's the transform set. But in general, all the settings have to match. So when I say crypto ISAKMP key VPN PA55, and I've got my encryption AES and the authentication pre-share and my Diffie-Hellman group, those need to match on the other router to which I'm creating this site-to-site IPsec VPN tunnel. So, and then we say VPN PA55, and now the address. And a common convention that you'll see is people will drop in the quad zeros here. And all that means is that I'm willing to communicate with any IPv4 address. However, we want to scope this down and be very specific. Specificity is a good thing when you're dealing with crypto. And I'm only going to be working with this key with this router, 10222, and that is not router 2, that is router 3. So that is all of my IKE/ISAKMP Phase 1 configuration. And in fact, they put it in a nice, they put it in a nice little bundle here in the configuration, right? So there are all of my default settings. I'm sorry, correction, not my default setting. There are all of my manually configured settings. The default settings, how do you see the default settings? And the chapter mentioned this command. It's a super cool command, right? And I'll just end all the way out. So all we would do is say show crypto ISAKMP default, I think it's policy. Yeah, default policy. And there we go. And so by default, right, if I didn't enter in any specific settings, right, like the 256 or the Diffie-Hellman, if I don't say, group whatever, here are the defaults. If I'm using AES, it's going to be a 128-bit key. It's going to use SHA. Authentication method would be RSA. There's my Diffie-Hellman group. It's going to choose 5 by default. And again, these are settings you don't want. And the lifetime is 86,400. And the lifetime is how long do the routers wait before they refresh the keying material? In other words, before they regenerate the keying material. And 86,400 is decent. I typically set mine to every 24 hours. I have the routers refresh the keying material to ensure that things are constantly being updated, right? Static is typically, you don't want to leave things the same for long periods of time. So I'll typically shrink that down to 24 hours. And that's 86,000 and 86,400 seconds. I don't know what that is off the top of my head. But anyway, we'll move on. So, but you can see here, right, the different default settings that you have, and it goes down here because if you're using, let's say you're using triple DES, right? So 3-key triple DES. You can see that it uses RSA and then Diffie-Hellman group 2, and this is super dangerous. So never ever, you should never be using DES, right? DES, never use DES, never use triple DES unless you have to. You should always use AES. All right, so let's drop back over to the packet tracer activity. So our IKE/ISAKMP Phase 1 is done, and that's ready to go. But that's not everything. Now we have to do our IKE/ISAKMP Phase 2 settings, where we're going to be defining the parameters for the IPSec tunnel. So let's dig in here and say crypto, IPSec transform set. And this is the transform set. Now this name, right, VPN set, that's arbitrary. I can use any name that I want here. So I'm going to say crypto IPSec transform set VPN-set. Now we get to the good part. So what are the protocols that I'm going to be using for my IPSec tunnel? Now, again, we get a nice condensed version of some choices here. I'm going to roll over to the real router in a second, but we get some nice condensed choices here. Now, remember authentication header and ESP, right? AH and ESP. AH only provides the authentication component. It doesn't provide confidentiality. In other words, there's no encryption with AH, which is one of the reasons you very rarely see AH used. Another reason you very rarely see AH used is that it doesn't work with NAT. And that's a huge problem. If you're doing a site-to-site IPSec VPN tunnel and you're using NAT, authentication header is not going to get it done, right? And so again, unless there's some legacy compelling reason that you have to use authentication header, you're never going to use authentication header because ESP does the authentication and the encryption. In other words, it provides the authenticity as well as the confidentiality that's required with the site-to-site IPSec VPN tunnel. And so ESP is where we're focused. And you can see right here the HMAC SHA authentication. So here's the ciphers that we can pick from. That's our encryption. And then here's the authentication hashes we can choose from, right, for the authenticity. Now, when we look at these, it's pretty cut and dry, right? Well, this is pretty straightforward. So I'm going to go ahead and say VPN set. Let me come down here. And we're going to say, what are we? ESP-AES and ESP SHA-HMAC. So I'm doing confidentiality as well as authentication, right, with the SHA-HMAC. But ESP does it all. So there's really no need to use AH, to be honest with you. Again, unless there's some compelling, backward compatibility legacy reason, you're going to probably use ESP. Now, I'm going to hit enter here, and my guess is that it's not going to take me into the mode selection dialog, and we'll talk about that. And it didn't. It leaves me at global config. Now, I hit enter, and that's it. For the packet tracer activity, that's fantastic. But the chapter talked about something very, very important. When we're talking about ESP, there are two modes of operation with ESP. And actually, let me step over. This is a good time to transition here. And let's get into global config. And let's say crypto IPSec transform set VPN-set. And I'll do a question mark here, and you're going to be amazed at how many options you have to choose from, right? So here are the options that we can choose from. If I go back over here real quick, you can see that we chose ESP AES. I didn't specify a key length here, or a bit length here, right? And then ESP SHA HMAC. And again, I didn't specify a bit length. When we look at the real options that you can pick from, you can see that this is probably one you're not going to use, right? Because remember, larger is always better when we're talking about bit size, right? About the bit length is what I'm trying to say there. And then here's the ESP, oh, sorry, I didn't want that. I want DES. Never use DES, never use DES, is ESP AES. So if I was to say crypto IPsec transform set ESP dash AES and do a question mark, now you see I get to pick the bit length. So I would always choose 256, and then you would always choose ESP dash SHA 512 HMAC. Now here's something that's interesting. If I have two settings, if I have these two settings here, right? The one for confidentiality, the other for the authenticity. And on the other router, let's say I had all of these things set. That's okay, because as long as I've got these two can negotiate and exist on the other router, they don't have to, so in other words, what I'm saying is these do not have to be identical. It doesn't have to be that only these two can be on this router and only these two can be on the other router. It's as long as those two are on both routers that it's going to work. So I could, on this router, say, oh yeah, and just in case it's an older router on the other side, I'm going to say AH-MD5-HMAC, right? And maybe the older router doesn't do ESP SHA 512, maybe it does MD5 HMAC. So as long as the other router has that for the confidentiality and this for the authenticity, we're good. We're good. So you'll notice it didn't take me to global config, and this was the config crypto transform set global config mode here. And we went to global config. We didn't come here, but it's very important to talk about this. Chapter touched on this, and this is a key component here of setting things up. You'll notice we have this mode setting that we can use, and I can choose transport mode or tunnel mode. Now, by default, Cisco routers use tunnel mode. And let me give myself some space here, because I'm going to draw something out for you. So by default, the routers use what's called tunnel mode. And so we'll put this up here. I'm going to say, and what are we going to do first? We'll do transport mode first, so because it comes first. So transport mode. So here is what happens in transport mode. And then down here, we'll say tunnel mode. And here is what happens, make it a little bit longer because there's going to be a little more. So in transport mode, you have your IP header, right? I mean, the packet has to know where it's going. And that's another key thing. We talk about a lot about IP. IPsec. IPsec is encryption. It's a layer 3 technology, right? It's a layer 3 technology. So we've got our IP header, and then we have the ESP. Remember, this is specific to ESP. AH is different. This is specific to ESP. We have our ESP header, and then we have our data. And then we have our ESP trailer. Our ESP trailer. And then we have the ESP authentication, ESP auth, right? That authenticity that we're using. All right, so here's what we have in transport mode. In tunnel mode, we have what's referred to as the new IP header. And all the new IP header is the source and destination information, right? Then we have the ESP header, just like we did above. And then we have the IP header again, the original inner IP header. And then I have all that data, right? Whatever data it is, and that is a terrible D. Have that data, and then we have the ESP trailer, just like we do above, trailer. And then I have the ESP authentication, ESP auth, right? To ensure the authenticity. Now, remember, the key here is we want encryption, right? We want confidentiality of this information with IPSec. But in transport mode, here is what is encrypted. That is all that is encrypted in transport mode. So in other words, the ESP header is exposed and the IP, the original IP header, is exposed. The only thing encrypted here is the data and the ESP trailer. Now, when we come down to tunnel mode, you've got the IP header, the original original IP header, and all the way down to here. So when we talk about tunnel mode, and the reason that they call it tunnel mode is because this new IP header here is prepended, and so everything behind it is tunneling based off of that information. It's no longer using this IP header. It creates a new IP header and it puts it here on the outside of the packet. And so that's why we say it's tunneling. Now, or tunnel mode. Now, this new IP header, it's still the same source and destination information from the original IP header, but we're encrypting the original IP header now, okay? All right, and it protects that. Now, in terms of the authentication, which I'll do in, what's a color that's going to pop here? Let's say green should be good. For the authentication, what is authenticated? Well, in transport mode, it's from here. I'm sorry, yeah, in transport mode, I thought I said the wrong thing. In transport mode, it's from there to there. This is what is provided authenticity, right, with the ESP authentication. With the tunnel mode, it comes all the way out here, right? It's going to protect all of the same information. And so that is the difference. Let's get AUTH. And that's the difference, right? So in terms of the authentication, we're authenticating the inner IP header, right? All of this information in here, including the inner IP header. So what's different? Yeah, is that we have this new outer IP header with the source and destination that was copied from the original IP header, and it's prepended to the IP packet. And that is how the information is being routed around, right? And tunnel mode is the more secure mode, and it is the default mode. So you may be asking yourself, well, I think that's great, Travis, but when would I use transport mode over tunnel mode? When would I use tunnel mode over transport mode? Why would I use one over the other? And this is a general rule of thumb. And this has kind of always been my experience, is I never use transport mode. Transport mode is typically when you're terminating at a PC or some, a server, right? You're at some node, some end node, okay? And that's typically what transport mode's all about. Tunnel mode is when you're going between router endpoints, right? Router 1 to router 2, or from your firewall, because you can do an IPSec VPN tunnel from a firewall to a router for a point-to-point tunnel. In fact, we're doing this from an ASA to an ASR, right? And you can do a point-to-point IPSec VPN tunnel here, right? And so this is where you see tunnel mode. It's between VPN, I don't want to use the word concentrator because there used to be an appliance called a VPN concentrator, but I mean, that's what it is, between VPN transit points here, right? Between these routers or between a firewall and a router. Whereas transport mode is more for a PC, like an end node, or maybe like a mobile device. That's typically your transport mode. So tunnel mode, this is where we want to be, right? And we're talking about router to router, so that's what we're going to use. Again, it's really important to understand the semantics behind some of these choices. Now, the other thing with tunnel mode, and you notice I said it was, they put an outer IP header and then we've got the inner IP, and I think the book mentions this, but really what it is, it's called IP, in IP, for obvious reasons, right? It's IP inside of another IP. And that's another way that tunnel mode is referred to. You'll hear IP and IP because we're slapping this outer IP header on here that is being used in place of the inner IP header. So let me go ahead and clear that off there. Pull this back up. Let's transition back to our activity where we've been logged out. And so I get the bonus lab, Cisco CON-PA 55, which means I have to enter all this information in again, Cisco ENPA 55, just the password information. So now let's go into global config. And we're going to do the crypto map. I did the transform set. I want to make sure do show run. And yeah, we did do that last. There it is. So there's my transform set, right? You'll notice it doesn't say the mode, right? And the reason it doesn't say the mode is because the default is tunnel. In fact, let's make sure that that's the case. So if I say mode tunnel, and then I say do show run, does it show me that it's tunnel mode? Because remember, it does. So interesting, right? So let's change that. Let's say mode transport and then do a do show run. So this is one of those, remember I said 99.999% of the time is that Cisco iOS, it's going to put it in there, it looks like. Looks like it's going to put, no matter what you put in there, it looks like it'll put it in there. And maybe it was in there before I had put it in there. It's a possibility. But 99% of the time, the default, Cisco's not going to show you the default, right? And it looks like this may be one of those cases where that is not the case. And so hold on one second here, because now I'm curious. So we're going to say crypto IPSec transform set ABC. I'm just going to use a different name. And we'll say ESP-AES, and then what are we going to use? We'll use the 512. We'll just use this one here, ESP HMAC12, copy and paste. If I hit enter and I say do show run, because I want to see, did I type in tunnel? Where's that transform set at? And so there you go. So that is proof that that is the default because it put that in there for us. We didn't have to type it in. And this is also one of those cases that's the exception, right? Here's an example of where Cisco does put the default mode or the default setting in the running config. All right, so back over here, we're going to do our crypto map now. And the crypto map, think of it as like in the map, they couldn't have chosen a better word, right? Crypto map, it's a guide. It's a guide for the IPSec policy to look and say, okay, and let me first get the crypto map and VPN-map, and we're going to use 10 IPSec ISAKMP. So it's a crypto map. It's a guide that tells the crypto map, here are the different settings that we're going to be referring to and using as part of this map. So, and description's not one of them. I'm just going to put it in here, connection to R3, because I'm wondering if they have points maybe dependent upon that description. I don't think so, but we want to make sure we get it in there. Okay, so who is my peer? Who is this crypto map going to be used with? Well, it's 10.2.2.2. What transform set is this map going to be using? Well, it's going to use the one that we just created, VPN-set. And how am I identifying the interesting traffic? How am I matching the interesting traffic? I'm using extended ACL 110. And that's it. And now I go into serial 000, and we say crypto map VPN-map. Now you can see that ISAKMP is on, and this is going to do a couple things. Right now, any traffic going from the R1 LAN to the R3 LAN is not going to get there. And I'm going to prove that to you. We're not just going to make a statement, right? I'm going to prove it to you because you may be saying, oh, well, since the tunnel's not set up, the traffic, it'll still work. So let's try it. Ping 192.168.3.3, and it's not going to work because we have activated the crypto map on the serial interface. So now all traffic that is showing up, and my pen is not working, there we go. all traffic that is showing up at router 1, right, that is going to egress out this serial 000 interface where the crypto map is defined, all of that traffic now is being inspected, and not inspected in the sense of a context-based access control. It's being inspected by the crypto map policy to determine, where's it at? Does the traffic match that whoops, I didn't mean to line that out there. Does it match that ACL 110? And so here we go. We have to refer to the ACL. And the answer is yes. The source and destination for all of that traffic that we just generated here, these pings, is coming from a device on the source subnet going to a device on the destination subnet. And so router 1 right now is saying, okay, if that's the case, I'm encrypting it based off of my transform set settings in VPN-set using AES, where do we go? Using ESP AES and ESP SHA HMAC for my confidentiality and authenticity, right? And so that is what is going on right now. And here, let me prove to you that that crypto map is only going to impact the traffic between the R1 LAN and the R3 LAN by pinging R2's PCB. And what we're going to see, and we're going to get faked out here at the beginning because I may have to ARP out real quick and get the default gateway information. And the first request is going to time out, but subsequent requests are going to work. And so again, let's prove, and there you go. Right, so that's going to work. It's going to work beautifully. All right, so now what we need to do, we did the interesting traffic with the extended ACL. We configured the IKE/ISAKMP Phase 1 policy on router 1. We configured the IKE/ISAKMP Phase 2 policy on router 1. And then we took and we configured the crypto map and configured and placed that on the, we'll say, publicly reachable interface, the outside interface there on the router. And now we're going to do the exact same thing on router 3. And in fact, before we do that, let's see, can I ping PC1 from R3's LAN? So from PCC, can I ping PCA? What do you think? So maybe it's just going to miss the first 2. Maybe the first 3? Why is it not working? Yeah, because, and you got to think this through, right? Because you may be thinking to yourself, oh, yeah, that's going to work because the traffic is coming over here. It's not going to match the ACL, right? And you're right. The ping request, or the ICMP, the request, yeah, the request isn't going to match the ACL. But what's going to match the ACL? The echo reply that has to go back, because the echo reply is going to be from that IP going to this IP, and that is going to hit that crypto map right here, and the crypto map is going to say, whoa, hold on, all traffic, I need to check, do you match my extended ACL? And it does, therefore it's encrypted. It's not understood. It's going to get over here, and it's really not. It's going to get here, and router 3 is going to have no idea how to decrypt that traffic, and so that's a huge problem. So let's go ahead now and let's solve that problem. And you can see we're at 50% down here in the, the lower right. My guess is it's going to be 50-50, right? 50 for router 1, 50 for router 3. And let me pull this back just a skosh. All right, so here we go. And I'll move router 3 up a little higher here. So here we are on router 3. Whoops, here we are on router 3. Cisco Con PA55. Go to privilege exec with the enable Cisco EN PA55 and show license. Did we apply the license? Show license all. Did we apply the license here? Actually, show versions better. And yes, security K9 eval license is in play. So from here, we can, and again, I'll move through it a little quicker here. What do we want to do first? I want to create my extended ACL. Whoops, sorry. Access list. Let's go 110. Is it? We have to use the same number again. Where's it at? Yeah, access list 110. Permit. and IP, but here it's backwards. Remember, 192.168.3.0/24 going to 192.168.1.0/255. So there's my ACL, right? That's the interesting traffic I'm going to be matching and encrypting, okay? And what do we got next? So next we're going to do the ISAKMP, or I should say the IKE/ISAKMP Phase 1 setting. So crypto, ISAKMP, and policy 10. The encryption is going to be AES 256. The auth is going to be pre-share for the key. Our Diffie-Hellman group is going to be 5. We're going to exit out. We're going to say crypto. Having problems spelling today. Crypto, ISAKMP, key, VPN, PA 55. And you want to be very careful here because you'll never get, and that's the other thing, you can never get to Phase 2 unless Phase 1 successfully negotiates. Because remember, Phase 1 is all about protecting the keying material that is ultimately going to be used. So that's why we want to make sure that if we don't successfully negotiate Phase 1, that we just don't send the key and say, oh, all right, well, we'll send the key anyway. And the address is going to be the router 1 outside interface IP address. All right, now we're going to go ahead and do the IKE/ISAKMP Phase 2 component here, and we're going to say crypto IPSec, because these are the IPSec settings, transform set VPN set ESP AES, and then ESP SHA HMAC. And I don't have to say mode tunnel because that is the default. Tunnel mode is the default. So now we come to the crypto map, and this is VPN-map, and it's going to be number 10, IPSec ISAKMP. And here's again where we simply say this is our guide, right, as to how this map is going, or what things this map is referring to in order to function when it's applied to the serial interface. So I'll put my description in here, VPN. What is it? VPN connection to R1. And then we've got set peer, right? So who's my peer? 10.1.1.2. We're going to set the transform set to VPN-set, which is the one that we created as part of the ISAKMP/IKE Phase 2. And then the interesting traffic is going to be extended ACL 110 is going to be identifying that interesting traffic for us. Now I'm going to interface serial 001, and we're going to say crypto map VPN-map, and it is case sensitive, the name. All right, so the map is up. Or I'm sorry, I should say the map is applied. I don't want to say up. The map is applied, and the ISAKMP is on. So if that's the case, I should be able to say show crypto. And here's some good commands. Show crypto IPSec SA. So in other words, show me the Phase 2 security association, right? Let me see, is it working? Okay, well, it looks as if things are good here, right? I mean, this gives you the impression, all right, local endpoint, and I can see it, if I was encrypting stuff, it would show me that, and that this would be working, but we're not seeing any encrypted packets here. And if we roll down, what are they? I'm pretty sure they're going to have us do, okay, so show crypto IPSec SA. Notice number of packets encapsulated, encrypted, decapsulated, decrypted. It's all set to 0. And this is one of the tricky things with the crypto map is you're not going to see your packets encapsulated, encrypted, decapsulated, decrypted. It's not going to increment until what? Yeah, until I generate some traffic to be encrypted or decrypted. So how do we do that? Well, I could come over here to PC1 and I can say, all right, can I ping PC2? Yeah, see, that still works, right? So the IPSec VPN tunnel didn't break me getting to unencrypted destinations, right? Where like there is no IPSec VPN tunnel being terminated. Now let's ping PC3 over, or PCC technically, over on the R3 LAN. So I'm going to generate some interesting traffic, and let's see what happens here. Boom, and there you go. And now the tunnel, not only is the tunnel up, but we should see, and let me come over here to router 3 since I don't have to re-log in. Now when I hit show crypto IPSec SA, there you have it. 3 packets made it out of the 4 that we sent. Remember, the first one timed out. And now we see that traffic is now being encrypted and decrypted. So, but let's prove that that's the case. So if I come back, because I didn't do this before, and let me actually do the ping-t. So if I say ping-t 192.168.2.3, let's ping PCB over on the R2 LAN. And this is a continuous ping. And I'm going to log back in here to router 1. We're going to say Cisco Con PA55. We're going to say Cisco EN PA55. And we're going to say show crypto IPSec SA. Take a look. Only 3 packets have ever been encrypted or decrypted. In fact, if I bring this over here and we pull the PC up, you can see that traffic is still flying, right? But it's not being encrypted. And that's conclusive proof that we are not, the crypto map is getting the traffic. It looks at its guide. It looks at the map settings, right? And it looks at that match address 110 and says, yeah, this isn't interesting traffic to me. I'm not interested in encrypting this traffic and sending it via the IPSec tunnel, right? And it's not going around here to router 3. It's going to router 2. However, if I change this command and I say 3.3, right? So now that is being encrypted. And let's see if I give myself a little more room to work here. Now take a look. You can see it's 11 packets. Now it's 14 packets. And so the encap, encrypt, decap, decrypt, and this is how you check, right? This is how you validate once you've set up a tunnel. Hey, is it truly encrypting and decrypting the packets like it's supposed to? And this shows us beyond a reasonable doubt that is the case. Now you can see that we're at 100 out of 100. There's 2 additional things I want to talk about, and I'm going to make it brief, right? Because I know that this has been dragging on here. So, but these are critical concepts when you go to move forward in a security sense in the Cisco world. Now, remember I talked about we can do the crypto map, and I just spelled crypto wrong. We can do the crypto map, right? We can do GRE IPSec, and we can do an SVTI, Static Virtual Tunnel Interface. And remember, this is kind of the legacy way to do it. This is still a very common way to do things, and this is sort of the best way to do. And again, remember, these all have something in common. They are site-to-site. They're site-to-site, okay? Now, SVTI, I want to give you a resource. I'm going to point you to a resource here, and this is a brilliant resource. So, and I'll leave this up here because we're going to go back to that. So, an overview of site-to-site Cisco VPN technologies. If you go to ciscolive.com, this is free. You can access these sessions for free. This was from the 2016, whoops, I'm still drawing. This was from the 2016 Las Vegas Cisco Networkers. This year it's going to be in Orlando. And this session was an amazing session. You can watch the video, and you can download the session presentation, right? All for free. And it's BRK SEC-1050. Right? And these guys did an amazing job. And this is a CCNA level based off of the number here. You can say 1,000. This is a CCNA level introduction into the different site-to-site VPN technologies. And if I was to pull that presentation up, we're 5 pages in if you look down here. So, but here's the virtual tunnel interface. Now, there are 2 types, but the static, and you can see there's 2 types, the static VTI. So here it is. It's IPsec tunnel mode between your VPN peers. Simplifies the VPN configuration. There are no crypto maps anymore. There are no ACLs anymore. And there's no GRE to configure anymore. It doesn't get much easier than this. And it still provides the same level of security between the endpoints. Again, it simplifies your VPN design. There's a one-to-one relationship between the tunnels and the sites, right? So it's point to point. It's a more scalable alternative to GRE. Supports quality of service and multicast and other routing functions that you used to have to do. So like multicast and broadcast, you used to have to use GRE, right? With VTIs, and specifically the static VTI, you don't. So I highly recommend this session. The drawback is there's limited interoperability with other non-Cisco platforms. And so here you go. Here's some additional information about the SVTI. Again, can't recommend this session highly enough. It's free. I would definitely go check it out. And then the final thing I want to talk about is I keep stressing that site-to-site, 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 right? It's a point-to-point tunnel. So let's think of it like this. What if we had, and let's do this, I'll get the pen back. What if I had a site here, and let's say that this is New York, and this is my headquarters office, whoops, my HQ, and this is San Francisco. But what happens now when I put an office in London, and they've got an internet connection, and I'm going to put the big internet cloud, I'll put the cloud here, right? And these guys are connected into the cloud here, and these guys are connected in San Francisco. London's connected in, and then let me do this. I'm going to say that this is Spain. We have a site in Spain, and Spain is connected in. And then I've got a site in Siberia, right? And I think you can see where this is headed. And then I've got a site over here. Whoops, I didn't want a cloud. I wanted a router. In fact, let me see if I can, there we go. And this is Japan, right? And I'm bringing all these sites online now, and they're all connecting into the internet. And they're using whoever the provider is. The provider is irrelevant in this scenario, right? And I want this IPSec VPN tunnel between these guys. And so I set it up, and I do just what I did right here. But then we bring London online. And your boss tells you, okay, Travis, I need you to set up, I want to make sure that we can go from the New York office to London, just like we do over the IPSec VPN tunnel to San Francisco. And I want the San Francisco office to be able to go to London, just over an IPSec VPN tunnel, just like we're doing today. Well, how are you going to do that, right? Well, now you're going to have to get back onto router 1, and you're going to have to configure an IPSec VPN tunnel between London and router 1. You're going to have to get back on the San Francisco router, and you're going to have to configure an IPSec VPN tunnel between, excuse me, between San Francisco and London. And then you're going to have to get on the London router, and you're going to have to go create it to New York and then to San Francisco. And I'm not going to go through all of these because I'm sure that you're getting the gist of what is about to happen here. So now you open up a site in Japan, and your boss says, I want to be able to go directly from New York and from San Francisco and from London to Japan. So you've got to get back on the New York router. You've got to get back on the San Francisco router. You got to get back on the London router. And then you got to get on the Japan router. You got to configure all of these point-to-point. So full mesh is what we're getting at here. You're creating this full mesh because what you don't want to have happen is, let's say that the Spain office came online and you created a tunnel initially, and I've seen things like this, similar to this, that here is your IPSec VPN tunnel, that it goes from Spain to San Francisco. And then you bring on the tunnel between London and New York, right? And in order to make sure that things are secure, you basically say that all traffic from London has to go to New York. So when London wants to talk to Spain, what is that going to look like if these are the 3 VPN tunnels? Yeah, traffic from London is going to go transatlantic to New York, is going to go cross-country to San Francisco, is going to go cross-country again and transatlantic again to get to Spain. When all I wanted to do was go from London to Spain, literally across, and what is that, the Gibraltar Strait or whatever it's called there. So, I mean, again, this is a very short hop right here, right? But what have we just created? We've created a monstrosity where my traffic from London has to go to New York to San Francisco, across the US again, and across the Atlantic Ocean again to get to Spain, when this is all we wanted to do, right? So in order to maybe avoid any routing issues, we do a full mesh, but then we run into that equation, n times n minus 1 divided by 2. And, oops, sorry, n minus 1 divided by 2. And this is that full mesh equation where we end up with this sort of, linear increase in the number of point-to-point tunnels I have to create. And so when we're talking about site-to-site, right, and we're talking about point-to-point, and site-to-site is, think of it as point-to-point, right? Crypto maps are good. GRE IPSec is better. SVTIs are the best, but they all fail in one common aspect, is they're point-to-point, right? And that is where dynamic, and I guess I'm going to have to wipe all this out here, and this is where dynamic multi-point VPN, DMVPN, comes into play. And the text does a brief mention of this, right? Talks about DMVPN, and this is created by a gentleman by the name of Mike Sullenberger. And this guy is wicked smart. I had the opportunity to sit with him for an hour one-on-one at Cisco Live in Vegas a couple years back, and I sat down, I said, I just want to talk about DMVPN with you. It was the second time I've been able to sit with him, but one-on-one, this was the first time. And my question to Mike was, how did you come up with this idea? And he said that he was working in the Cisco TAC at the time, way back in the day, and there was a customer that he was helping troubleshoot an issue, and they had hundreds of site-to-site IPSec VPN tunnels. And he started to look at that as to how could he resolve this issue. And this is one of the reasons he is a distinguished systems engineer. And that is not a title that is given out lightly. Again, he is the creator, right? He is the brain trust behind DMVPN. And if you go back to the Cisco Live site and you search the view all sessions, there's a search feature at the top. Type in DMVPN. He has presented, I think I've been to 5 Cisco Lives in a row. He has presented DMVPN at every single Cisco Live. And again, the guy is incredibly brilliant, right? So what is DMVPN all about? Well, it's dynamic multi-point VPN. So what that means is, let's go back to the scenario where New York City is my headquarters office, right? And everything above this line we're going to ignore, okay? So New York City is my headquarters. Here's San Francisco. And then I've got an office in London. And here's the internet. And everybody's dialed in here. We've got our commodity, super cheap, right? Super cheap internet connectivity, right? London, we'll say Japan is connected in. I can't remember who else we use. Siberia. And I don't know why I keep doing the cloud over there. And then we'll say that this is Texas. We'll switch it up a little bit, right? And here's my headquarters in New York. In other words, here's the hub of my network architecture. And so DMVPN uses multi-point GRE and the next hop resolution protocol, and you can use IPSec, but again, remember, it's not required, but we're saying that this is the internet. You would be nuts not to use IPSec here, and here's how this works. Is dynamic multi-point VPN says, everybody, these are spokes. Everybody is a spoke site. If you're not the hub, you're a spoke. And everybody is going to create an adjacency from a DMVPN perspective to the hub. And real briefly, there's 3 phases here, right? And I'm talking about phase 3 DMVPN. So everybody creates an adjacency to the hub. So from a configuration perspective, you're only creating one secure tunnel, right? Technically in the config, it's one secure association and it's to your hub. And in our case, that's in New York City. Now, here's what happens when London, and actually I'm going to change, that's not Japan, we're going to say that that is Spain, right? So now here's what happens. All of these sites, they only create an association with the hub, but because of multi-point GRE and the next hop resolution protocol, here is what is about to happen. London says, I want to access the server over here in Spain. The first packet shows up at the hub because that is who London knows about. It knows about the hub. The hub, using the next hop resolution protocol, looks into its mappings and says, whoa, 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 wait a minute, London, hey, you already know how to get to Spain. Here's the information you need to do this, to go direct. And here's what it does. Because again, Spain is connected to the internet. London is connected to the internet. The hub, which is also connected to the internet here, basically gives London the information to stand up a spoke-to-spoke tunnel. And that is exactly what happens. A spoke-to-spoke tunnel gets stood up. And then this tunnel is no longer dependent on the hub, right, to go through the hub to create the tunnel. It simply creates it by itself with the router in Spain. So the router in London goes directly to Spain. It doesn't go to New York and then to San Francisco and then to Spain. It goes from London to Spain direct, and all with a single stanza of configuration on the hub router and on the spoke routers. In fact, you can deploy these spoke routers, you could configure them, ship it to the remote site, plug it into the internet, and it's going to go out and it's going to find the publicly routable address on the internet for the hub router, and it's going to stand that tunnel up for you. And this is in a multi-point scenario. And again, it's all about use case. If you only have 2 sites, do you need DMVPN? No, you don't, but you need to consider, am I going to be adding additional sites? And if that's the case, do I have a enjoyable, fun time getting onto all of these routers, creating all of these different IPsec individual point-to-point tunnels? If the answer is yes, then okay, you need to stick with point-to-point, right? And stick with the crypto maps or stick with the SVTI or do a GRE over IPsec, right? You can do that. If you think you're going to scale out, and I worked on, and this was about 6 years ago, I worked on a configuration where the customer had 4 hub sites across the globe, 90 or over 100 sites in all. And I mean sites in Africa, sites on every continent. And it was an insane configuration. You definitely want DMVPN there, right? You definitely want DMVPN because there's no way you're going to set that up using point-to-point or site-to-site VPN. The configuration would be thousands of lines long trying to do something like that with point-to-point IPsec VPN tunnels. So that is DMVPN. And again, I'm going to take us back to our main screen here. I'm going to clear that off. So what did we talk about in this tutorial? We talked about a lot. And again, all of it critically important from a CCNA security perspective. We talked about the crypto map. We talked about the IKE/ISAKMP Phase 1. We talked about the IKE/ISAKMP Phase 2 settings. We talked about the larger is always better in a general sense with the bit size, the bit lengths that we see that we're presented with that we can select from. We talked about the fact that this is a point-to-point solution. So if you've only got 2 offices, okay, yeah, great, this is going to work beautifully. If you've got more than that, you need to consider looking at DMVPN. We talked about the GRE IPsec. We talked about the SVTI. I gave you some additional resources that you could run down to expand your knowledge about some of the different choices that you have to make. And again, lastly, we talked about DMVPN Phase 3. And there's 3 phases. 1 and 2, typically those are legacy, right? 3 is where you want to be. And when I spoke to Mike Sullenberger, he said there really are no plans for a Phase 4, that it's just going to be Phase 3 and it's going to be continued to be improved. All right, that wraps up this packet tracer tutorial and solution set for activity 8.4.1.2 on site-to-site IPSec VPN tunnels. I hope this has given you guys a good, well-rounded intro into the world of site-to-site IPSec VPN tunnels. And that's all I've got. Enjoy your weekend, and I will talk with you soon.